yesterday we have discussed and proved solenoid as a solenoid equivalent to a dipole magnet. Successfully we have proved it. Right. Today the next new topic in magnetism, that is terrestrial magnetism. Terrestrial magnetism is Earth as a magnet. There are several evidence that says that Earth is a magnet. For example, when a magnet is freely suspended on the surface of the Earth, that dipole magnet will show the north and the south direction. When it comes to rest in north and the south direction, this is the best proof that Earth itself is a magnet. The dipole magnet's north pole is directed towards north pole of the Earth, and its south pole is directed towards south pole of the Earth. Because everybody knows that magnet has certain properties. It has directional property, and like poles repel each other, and unlike poles attract each other. When a magnet whose north pole is pointing towards north of the Earth means at the north pole of the Earth, the polarity is that of south. And at the south pole of the Earth, the polarity is that of north. That is why a magnet, when it is suspended on the surface of the Earth, it comes to rest showing two directions because its poles are being attracted by the poles of the Earth. Right? Another example is that when we make magnetic lines of force for a magnet, keeping the magnet on the surface of the Earth anywhere, the lines of force is like this, and there will be two neutral points formed like this. Right? When the magnet whose south pole is pointing towards the south pole of the Earth, or north pole is pointing towards north pole of the Earth, this is the actual north pole. And the actual north pole, right? Actual south pole, right? This is the actual south pole where the polarity is north. This is the actual north pole where the polarity is that of south. From the Earth's north and the south, from Earth's north pole, that means at the south pole of the Earth, the polarity is north, from where the magnetic lines of force are starting and going towards the south. Because magnetic lines of force actually starts from the north pole of the Earth, and it is entering into south pole. This is the condition. Right? When you learn about the magnetic lines of force, you will understand it. Right? This is the magnet, a dipole magnet. These lines of force are due to the magnet only, but these lines of force are due to the Earth as a magnet. So between these two, there are 2 points are formed. At these points, if we place a magnetic needle, that will show any direction. That does not show north-south direction. It means that these points, at these points, the field intensity is 0. Right? Between the magnet and the point where the magnetic field intensity is 0 is called a neutral point. Neutral points are formed on the surface of the Earth. When we place a magnet, this is the best proof to show that the Earth is a magnet. So these are the 2 proofs we can say that Earth is a magnet. Right? So at the south pole of the Earth, the polarity of the Earth is that of north, and the north pole of the Earth, the polarity is that of south. That is why the lines of force are actually starting from south and is entering into north in the case of Earth. But in the case of a dipole magnet, always you will see that the lines of force are starting from north and ending into south. But in the case of the Earth, the lines of force are starting from the actual south pole of the Earth and it is entering into the actual north pole of the Earth. Why that? Because at the actual south pole of Earth, the nature of the pole is that of north. And at the actual north pole of the Earth, the nature of the pole is that of south. This is the reason why. Right? Now it is shown that there are 2 axes here shown here. Axis of a magnet is an imaginary line joining the north and the south pole of that. Right? A magnet also can have an axis. Suppose if I join this north and the south pole of this magnet by a straight line, imaginary straight line, that is the axis. Axis of a magnet is starting from north pole and it is sending a south pole, or an imaginary line joining north and the south poles of a magnet is called its magnetic axis. In the case of the Earth, there are two axes. One is magnetic axis of the Earth, and the other is called a geographical axis of the Earth. Both these axes will never coincide, but there will be an angle between that. At any place, there will be an angle between the magnetic axis and the geographical axis of the Earth. So this is the geographical north and the geographical south joining with the imagined line, what is called geographical axis. Other is called magnetic axis. So every magnet, even Earth also has an axis. Every magnet also has an axis. What is an axis? It is imagined line joining the north and the south pole of a magnet. Earth is also magnet, hence Earth also has an axis. But in the case of Earth, there are two axes. One is the magnetic axis of the Earth, and the other is called geographical axis of the Earth. Magnetic axis and geographical axis never coincide each other, right? So next, magnetic axis and geographical axis. Next is magnetic meridian. Magnetic meridian is a vertical plane passing through the magnetic axis. At any place you are standing at, you can make the magnetic axis. Magnetic axis is made. Suppose you are standing at a place, you have a magnetic needle, right? Place the magnetic needle at that place and mark the north and south pole of the magnetic. Magnetic needle means that can freely move. It is inside a glass covering and all, and it is actually suspended with the help of a point edge. That means very sharp point. It is suspended, so it can deflect, right? Freely deflect. If a magnetic needle is placed at anywhere on the surface of the Earth, it will deflect and comes to rest, showing north and south direction. At the north pole of the magnetic needle, put a mark there, and at the south pole also put a mark there. Now remove the magnetic needle and make a straight line. And this straight line is what you call the magnetic axis of the Earth at that point, right? On that magnetic axis, you can place a vertical plane like this. A vertical plane is placed parallel to the magnetic axis, right? So this is what is called magnetic meridian at that point. Magnetic meridian is a vertical plane that you place along the axis. So plane is vertical, remember that. In the same way, there are methods used to find the geographical axis also. So it is a big procedure. Following that procedure, uh, we can identify the geographical axis at a place also. So on that geographical axis also, it's a vertical plane like this, right? So that is called a geographical meridian at that place. So on the surface of the Earth, anywhere you can place, you can create the magnetic meridian plane or geographical meridian plane. As a matter of fact, there are infinite number of magnetic meridians because anywhere on the surface of the Earth you can place that. Because a vertical plane that is passing through the diameter of the Earth, that means the magnetic axis of the Earth or geographical axis of the Earth, any number of vertical plane you can place anywhere you are standing at, right? So the number of magnetic meridian and geographical meridian that you can create on the surface of this infinite number of that. Am I correct? Infinite number of magnetic meridian there, infinite number of geographic meridian there. But you will see one thing, that between these two planes there is an angle between that. These two planes will not coincide. As I said, the magnetic axis and geographical axis never coincide each other. These vertical planes also never coincide each other. There will be always an angle between these two planes. Am I correct? So these are the things about it. This is magnetic meridian and also geographical meridian. So that also done. Now next is elements of magnetism, elements of Earth's magnetism. So we have already studied about the magnetic materials. Magnetic materials are iron, cobalt, and nickel, using which we can create magnets. But magnetic elements are a different thing. These are magnetic elements at a place. These are quantities which completely describe the magnitude and direction of the magnetic field of the Earth at a place. They are called elements of Earth's magnetism. Elements of Earth's magnetism are three in number. One is magnetic declination, other is magnetic inclination, and other is horizontal intensity of Earth's field. using which we can understand the direction and magnitude of the Earth's magnetic field at a place. These three quantities determine what is the magnitude of the Earth's magnetic field and also the direction in which it is acting. So remember once again, magnetic declination, magnetic inclination, and the horizontal intensity of the Earth's field. Let us now discuss what is called a magnetic declination. Magnetic declination is the angle between these two planes. This is the geographical meridian plane, and this is magnetic meridian at a place. You can create that, right? Anywhere you are standing at, you can create these two planes. Between these two planes, there is an angle between, and this is what is called magnetic declination at a place. So magnetic declination at a place is the angle between the magnetic meridian plane, vertical plane, and the geographical meridian, vertical plane at a place where you are standing at. That is what is called magnetic declination. Other is magnetic inclination. Magnetic inclination means if you suspend a magnet in the magnetic meridian plane. This is magnetic meridian plane and this is geographical meridian plane. Now I am separating the magnetic meridian plane like this. It's a vertical plane only. On the vertical plane at this point, if you suspend a magnetic needle like this, magnetic needle means that can vibrate, that can deflect, right? This is the axis of that. In that condition, you will see that this magnetic needle will make an angle with the horizontal. The axis of the magnetic needle will be in the vertical plane. That is in the vertical plane. That will be neither horizontal nor vertical, but it will be standing or at rest, making an angle delta with the horizontal of the magnetic meridian plane. And this angle made by the magnetic axis, horizontal of the magnetic meridian plane is called angle of inclination, or sometimes it is called angle of dip. Am I correct? The magnet is standing in a direction that is the actual, that is the total magnetic, that is in the direction of the total magnetic field of the Earth. Magnetic needle is standing at this position. It is in equilibrium. That means now this magnet is in the resultant, in the direction of the resultant magnetic field of the Earth. So this is the resultant magnetic field. That is what is denoted by kappa. Resultant magnetic field makes an angle delta with the horizontal, and this is what is called angle of dip at a place, or it is called angle of inclination, right? Now, what is horizontal intensity of the field? That is also very simple, because the resultant intensity, sometimes in some books it is written as capital R, some books it is written as capital I. Am I correct? R can be resolved into two components. One is along the horizontal direction, other is along the vertical direction, right? So R along the horizontal direction is that component is given by H. H is equal to R cos delta, and the vertical component is the Earth's field. Vertical component of the Earth's field means the resultant field of the Earth is equal to R sine delta. So this part is called horizontal component of the Earth's field. In most of the calculations, we will take horizontal component. The magnetic field on the Earth that we consider is most of the time as a horizontal component. That is equal to R cos delta. What is R? R is the resultant magnetic field at a place, right? Resultant magnetic field at a place can be resolved into two components. One is H and other is H is equal to R cos delta, and V is equal to R sine delta. What is delta? Delta is the angle of inclination at a place, right? Okay. Then we will say that then we will say that this one H is equal to R cos delta, V is equal to R sine delta. Squaring and adding, we will get R square sine square delta plus R square cos square delta is equal to H square plus V square. Squaring and adding, right? That is R square into sine square delta plus cos square delta is equal to 1. That means that R square into 1 is equal to H square plus V square. The value of resultant magnetic field at the place can be calculated. R is equal to H square plus V square. Also, we can say what the equation 2 by 1. This is equation 2. Equation 2 by 1, we will get tan delta is equal to V by H. V is the vertical component of the Earth. Am I correct? So at equators, suppose when you are standing at equator with a magnetic needle, it will be quite horizontal. When we go towards the pole, you see there is an angle. That means one pole will be going up, and its angle goes on increasing. When you reach at the pole, it will stand like this. That means there the angle of dip is 90 degree. But at the poles, it is quite horizontal because the angle of inclination or angle of dip is equal to zero. So at the poles, the angle of dip is 90 degree, and at the equator, the angle of dip is equal to zero. Right? That can also be proved here. At equator, delta is equal to zero, and at the poles, delta is equal to 90 degree. At equator, see, delta is equal to zero. That means tan delta is equal to zero. That is equal to V by H. Therefore, V is equal to zero. Why V is equal to zero? Because H is maximum. Right? At the poles, delta is equal to 90 degree. You take a magnet from the equator to the poles, then you will see that at the equator it is quite horizontal. That means delta is equal to zero. With the horizontal, the uh, the resultant magnetic field is not making any angle at all. So at the equator, a magnet will stand very horizontal. But when we go from the equator toward the poles, you will see that one pole is lifting up, it is moving up. And when it reaches the pole, it becomes quite vertical. That is why we say that at the poles, angle delta is equal to 90 degree, and at the equator, delta is equal to zero. So this relation can be used to find that. So at the poles, at the poles, you see delta is equal to 90 degree. Delta is equal to 90 degree. Therefore, the value of V is maximum. How can it be maximum? By putting this value delta is equal to, V by H. H is equal to zero. Because at the poles, the component field is totally and completely vertical. In the same way, we can say at the equator, the component Earth's field is fully horizontal, right? So these are the 2 points you have to remember. So this is about Earth's magnetism, and this is the topic about. This is also sometimes called as terrestrial magnetism. Earth is a magnet. Everybody knows. There are several reasons cited by scientists time to time, telling that Earth is a magnet. The several reasons they are talking why Earth is a magnet, but the genuine reason is not so far available. Still, the research is going on why the Earth is showing itself as a magnet. So this is this topic about many things we have discussed. You can go through this video again and again, and you will understand everything. And both this vertical component and the horizontal components are useful for doing problems and all, right? Okay. That means suppose a train is moving from east to west, then the vertical component is being cut by the axis of the train. Axis of the train. That means so many axes there. Every axis, as it is cutting the magnetic lines, vertical magnetic lines or vertical field, and EMF is induced at the two ends of the axis of the train, right? So we can calculate the EMF induced there. And also an aeroplane with a wingspan is moving horizontally, then also in the direction of the horizontal field, if it goes, no EMF is produced. But when it cuts the magnetic field, either this is horizontal or it is vertical, then due to change in magnetic flux, EMF is produced. So this kind of questions are very common and also very famous that you can find in the textbook, right? So read the textbook very well and also follow uh, this video. You will understand many things, everything I suppose about Earth's magnetism. This is a topic about. Tomorrow I will come with a new topic. Till then, bye.